Maybe you can click. Yeah, it disappeared there, but it's cool. Okay. Okay, so I think we can start. I hope everybody. Can you hear me online? I guess, yeah.
Yes.
Thanks. So it's my pleasure to introduce today Professor Adi Zitrin. So Adi did his PhD at the Tel Aviv University under the supervision of Tom Broderst. Then he moved to Heidelberg as a postdoc under the supervision of Matthias Bartelmann. And then he got a Nobel Fellow at Caltech in US with Professor Richard Ellis. And then he got professorship at Ben-Gurion University in 2016. Adi is well known as a specialist of gravitational lensing. He led or was involved in many Hubble flagship programs on lensing clusters, such as CLASH, the Frontier Fields, or more recently, RELIX and Buffalo. He developed a unique and automatic tool for studying large sample of cluster. And on another side, he also held the record for the most distant galaxy confirmed by spectroscopy. It was at redshift 8.68.
Until you broke it.
Yeah, for a couple of years. But today is going to talk about strong lensing of transients by clusters of galaxies from cosmic telescope to cosmic microscopes. That's yours.
Thank you very much for the lovely introduction, Nicola, and thanks for the organizing committee for inviting me. It's really a great honor to be here. So I want to tell you today a little bit about recent developments in my fields of study, in lensing, strong lensing in particular. Okay. And that would be the main part of the talk. But in order to do that, I need to go through a little bit of history, which is great to do here in Cambridge, because much relies on stuff that happened in Cambridge. And some classical or traditional science that we've been doing with lensing, which basically refers to the past 20 years up until a few years ago, which is where the new exciting transient science began, transient with lensing. These are some of the agencies that fund part of the research. So let us go through some brief historical introduction. We go back here to Cambridge to about 1916. I guess many of you know the story much better than I do. I'm not an historian, but this is a lovely story. So we go back to 1916, where Eddington here started getting involved and interested in general relativity. Now, these were the days of the First World War. It wasn't easy to get the theory out of Germany to England, but William de Sitter was in a neutral Holland, managed to pass the material and the papers to the Royal Society, and through Dyson, Eddington got it, and was, until today, is considered to be perhaps the first to really realize and understand this theory all the way through. And Eddington understood, because the theory predicts a factor of 2 difference in the deflection angle of massive bodies, deflection of light near massive bodies, factor of 2 difference from the Newtonian calculation. So Eddington realized that in order to probe this, they could do an experiment and measure the deflection of light of distant stars behind the sun during a solar eclipse. Otherwise, you wouldn't be able to see the star. So you have to catch it when the sun is dark. And indeed, in 1919, after a crazy story where Eddington should have been drafted, but he refused to, and then Dyson convinced the authorities not to send him to jail because he was a Quaker and he would go and do the expedition on his own. So it's worthwhile keeping him outside of jail. And he did, and in 1919, there were 2 expeditions organized by Dyson and Eddington, one to Sobral in Brazil and one to Principe in West Africa. 2 different places, because in case one place is weathered out, both places ended up being weathered out, but they still managed to do the observation in the last few minutes and showed that stars are really deflected in the amount that GR predicts. And within a few days, Einstein became the celebrity we know him to be, and we know that GR is the correct theory. There's much more to this story. I encourage you to read it, especially the young ones. Okay, so what is gravitational lensing? So we have a massive object, according to GR, distorting space-time, which basically acts as a lens, because light rays from a distant object that wouldn't have gotten to us otherwise are now deflected towards Earth and get to us. So basically this lens, this gravitational lens, converges light rays towards us and thus magnifies the background object. So in the strong lensing regime, what happens in the sketch which we just saw, if we project it, then there are a few things that are noticeable. First of all, galaxies are magnified and sheared. The background galaxies, they are shifted away from the real position. There are a few appearances, a few images of the background source that appear. And another interesting thing, there's also a time delay in the light arrival time from the different images because of the different paths and different potential that the light has to go through. If the source is a bit farther away from the line of sight, then the effect is much weaker. It's called weak lensing. And I'll show you, we can only measure it statistically, but the background galaxies suffer from the same effect, and they are slightly sheared and distorted. Okay, here's a nice little video that shows, I think it's a black hole mass going through and creates an Einstein ring. So when there's a point mass or a symmetric lens and the source behind it, it forms an Einstein ring. And the reason I show this is because the next question, okay, gravitational lensing is nice, but how do we do science with it? And these simple equations relates the observable, which is the size of the Einstein ring, to the mass of the lens. So here in this simple equation, we basically showed that we can take an observable, a simple observable, just the size of the ring, and weigh celestial objects with it. Okay, this is amazing. But this is for a point mass, and most lenses in the sky are not pointless. So I'll explain to you in a second how we usually do it, but we sort of know what lensing is now. Let's talk a little bit about what we do with it. By the way, feel free to ask anything during the talk. Don't have to wait to the end. So the second part is to tell you a little bit how we model gravitational lenses as what science we have traditionally been doing with it. So the first thing is, we just mentioned, we have a possibility to weigh celestial objects. Now, celestial objects mostly consist of the invisible dark matter that we cannot see or weigh otherwise. So we have a method to map the invisible. Okay? So that's the first thing. So in the weak lensing regime, what we can do is we measure the electricity, the average electricity in different places around lenses. Okay? We have to measure it on average because we don't know the intrinsic electricity of each galaxy. So we just measure in some area what is the average electricity. And then we can translate it using a simple equation to the lensing observables, which are basically the derivatives of the potential. And then you get a large scale map, which is relatively low resolution. The constraints are at low resolution. And in the strong lensing regime, here's a nice demonstration. I think it's made by Phil Marshall and Thomas Zitrin of a candle lensed by a wine glass. And what we want to do is we see the observables, and now we want to do some reverse engineering, get understanding of what is the underlying matter distribution, right? So the way to do it, well, if we have an Einstein ring, it's easy. But if we have a cluster, which is a continuous matter distribution, the way to do it is pretty simple. We take Einstein deflection angle, 4gm over c squared r, and we basically translate the following sentence into a geometrical equation. We say all of these multiple images of a single family go back to a single source. That's the only thing this equation says. And through this, right, and if we expand it to we do the integral of the full field, then we get the mass distribution of the lens. So in practice, we get an image of a cluster. Usually we need HST to do that because the resolution is much better. And then our first job is to identify families of multiple images. These would be the constraints we would put in the equations, right? So each color here marks a different family. And then we need to take these families. We should measure the distances or estimate the distances, put it in the equation, and we get some solution. One famous, probably one of the first methods to do that is categorized into what we call non-parametric or free-form methods, basically not assuming anything on the underlying matter distribution, just taking the constraints and trying to find the solution that best describes this appearance of images. This is very novel in essence, it's model free, but usually we don't have enough constraints to get a proper solution. So the solutions are quite bad, often missing structure on small scales. What people have been doing, and this work this seems to work very well, but is model dependent, is to rely on simulations and say that the dark matter should follow, say, NFW halos, and take scaling relations for the galaxies from the fundamental plane, combine them together and get some total mass distribution, and then iterate on the parameters that best describe these functions. And this seems to work very, very well. We also developed our own method a while ago. This is based on some ideas that Tom Brothers had in the beginning of the 2000s. It's called light races mass. So basically we do the same thing. We take the cluster galaxies following some scaling relation, but instead of taking some symmetric artificial dark matter distribution, we smooth the galaxy distribution and we say, okay, this is now representative of our dark matter distribution because we assume that wherever there is mass, there should be light, or vice versa. And this simple procedure that takes less than 1 second on the computer works very, very well in reproducing the multiple images, as you can see. So these are the real data. These are the top row in each of these is the real data, and the bottom row are the multiple images produced by the model. So this seems to work very, very well. Now, again, we have to iterate on the free parameters and get the best fit model. Okay, so with these methods, about a decade ago, we got involved in the CLASH program, imaging 25 clusters with Hubble. Now, this more or less marked the transition from the period of analyzing individual clusters to analyzing larger sample of clusters. So we mass mapped, 25 clusters. We got the mass profiles. We confronted this with simulations. There have been some challenges to lambda CDM back then of over-concentration of halos that we sort of reconciled. And now there are new surveys that continue these efforts. So the first thing we said about lensing is that we can now map the dark matter distribution, the invisible distribution. Okay? That's the first thing I want you to remember. The second thing is that we have a lens, a magnifying lens, so we can actually see finer details at high redshift. Okay? And because of how the angular diameter distance behaves, it turns over at some point. At higher redshift, we can actually see finer and finer details. So we can reach 50 parsec resolution at redshift 5. Okay? That's quite amazing, just thanks to lensing. Another nice work, this is by Eric Julo, is that you could constrain cosmology with lensing, because lensing depends on the distance ratio, on the cosmological distances. So you can confront the redshift with the distance and put constraints on cosmology. This is also a major contribution of lensing, as you probably all know, time delays from quasars. So we mentioned that multiple images would show time delay because of the different light paths and path through gravitational potential, and the time delay is inversely proportional to the Hubble's constant, and today it indeed constitutes one of the leading constraints on the Hubble constant. So this is from the Cosmograil light curves of the 4 images, and you find the time delay and you get the constraint at H0. And as I guess most of you know, there's about a 5 sigma tension between the CMB results and the results from supernova calibrated with Cepheids and lensing. Supernova calibrated with Myra seem to be reconciling a bit the tension, but I guess it's still early to know. Okay, so that's the first front where lensing has traditionally been useful. Traditionally meaning the past, it's a relatively new science, so the past 20 years, maybe 30 years. The second front is high redshift galaxies. Okay? We have a lens, magnifying glass, so basically we can use this cosmic or natural telescope to observe further into the distant universe. And this has traditionally been used to break records of the highest redshift galaxies known, and fainter galaxies that have been found. And of course, that high redshift science, we have enough experts in the crowd that do that, have some urgent questions, such as how did the universe got reionized, whether galaxies produce enough ionizing radiation to do that, how did the first structure and galaxies form, is there a cutoff in the mass function, etc., etc. What are the physical properties of the first galaxies? So lensing can really help us do that. This is a sketch from Avi Loeb on how realization might have taken place. And we have a lens that magnifies background objects, hence we see more galaxies. right? So we should always use lensing. But before we shout that, we have to remember that when we look through a lens, the source plane that we probe is also smaller. So we cannot immediately say that we gain with lensing, right? We have to take this magnification bias into account. And in fact, if you do the calculation, you see that in order to overcome the reduction in source plane area that you're probing, the fainted slope of the luminosity function has to be steep enough. And apparently it is. So you go fainter with lensing, you gain more galaxies than you lose in area. So that's okay. So we do gain more with lensing. Okay, that's why you see that the lens luminosity function, the number density is always higher on the brighter end than the unlensed luminosity function. And this is why Hubble and James Webb are devoting a lot of time to observe lensing clusters. One of the reasons. So in the class survey, we found several of these very high redshift galaxies that are lensed. One of them is this one published in Nature by Wei Zheng, which photometrically we thought it's redshift 9.6. Recently, with Richard and Nicola, there was a paper showing that it's actually measuring spectroscopically at 9.1. This was found by Dan Coe, triply imaged galaxy at redshift 11. There's also a JWST program to observe it. The farthest known galaxy to date is this one, GNZ11 by Pascal Oesch. Is not lensed as far as we know, although it is slightly brighter for its redshift, slightly too bright for its redshift, but still probably not lensed and spectroscopically confirmed. Okay, so after clash, yes. Why is it brighter? I don't know. I don't think it's crucially too bright, but it is on the bright side of what you would expect. Maybe we're just biased to see the brighter things. You know, Richard, why?
It's a puzzle. It's so luminous, and they also say it's quite young, which doesn't have.
Right.
So it's a bit of a worry.
Yeah.
Is it starless? Sorry. Is it starless? Yeah, but its mass can be measured too. It's a bit, you know, it would have had to have formed its mass very, very quickly. So it is a puzzle.
Yeah. Yeah. So I don't know. So following the success of the CLASH program, Hubble then embarked on a very ambitious program using directionary time, this directed discretionary time, to observe 6 clusters to unprecedented depth using more than 1,000 orbits. This is called the Hubble Frontier Fields program. In this program, we found many high redshift galaxies. One of them is a redshift 10 galaxy, triply imaged that you can see here. We found, I'm just citing several results. We found a cluster of galaxies or proto-cluster of galaxies at redshift 8 that Nicola later verified the redshift of. We found, this is in the RELIX program already, there's a redshift 10 very long arc. Of course, with all these galaxies, you can build a luminosity function and answer some fundamental questions. Some say there's a turnover at faint luminosities. Recent work, including by Richard Boens and Richard Ellis, here claims that there's no turnover from what they see to faint magnitudes until now. But the key point here is that, you know, if you look at this last point and compare it with the blue one, this whole thing we gain thanks to lensing. So without lensing, you could only reach here. So this, I think this quite emphasizes why we want to use lensing for high redshift studies, at least statistically. Some other results, it helps us see emission lines in dust. This is a nice rotating galaxy paper by Nicola and Seiji Fujimoto in the ALSC program. And some of the fundamental questions, other than what I've mentioned, that we're trying to answer, or puzzles that are now on the high redshift front before I move on to the main part of the talk, are that, you know, we measure these emission lines at high redshift, usually Lyman alpha, that's the first one we did measure, but then we see also other meta lines. Some of them require a high ionization potential. I think, correct me if I'm wrong, I think that C4 is 54 electron volts. And we see C4 and we see helium-2. And we see nitrogen 5 signs of, right? 3, 4, maybe 5 sigma, but not something. So we think we might be seeing the missing link between, galaxies and these high-redshift quasars you hear about, which are basically AGN or sizes of AGN. In other words, is the ionizing field from these galaxies dominated by AGN or by POP3 stars, binary massive stars at high redshift, etc. Another fashionable thing now is to map ionized bubbles around these galaxies in which we saw emission lines. So basically look for overdensities of galaxies around them. If they reside in an ionized bubble, then the other galaxies should probably also show Lyman alpha. So that's some of the programs that are now being undertaken. I would like to highlight a nice result by our recent postdoc, Lucas Fortak. So one of the questions is we're trying to understand what's going on in these bubbles and around these galaxies. We're trying to look at the double-peaked Lyman alpha. Richard and students, Roman Mayer, also had a nice work about it, because the shape of the Lyman alpha profile tells us about, or at least can imply about several models of what's going on around these galaxies, such as expanding shells, outflows, inflows, etc. So Lucas found a very interesting object that shows a double peak as well, but it's the first object known in which the blue peak, right? There are many double peak Lyman alpha objects known. This is the first one in which the blue peak is significantly stronger than the red peak, and it's not completely clear why. Might be related to the angle in which we see it, or some very porous H1 density or distribution. It's not. We have some ideas, but it's not completely clear. But anyhow, it's a really nice discovery. Okay, so we talked about strong lensing and weak lensing, and the third thing I promised I briefly mention is micro lensing. Micro comes from the fact that the Einstein radius is usually of the order of micro arcsecond, and micro lensing is simply the case where we look at the background object, probably in the Milky Way, and there's a lens passing between another star, passing between us and the distant star, and then the light from the background star is magnified in time. This is now one of the most abundant methods to find planets around stars, because then you would get a secondary peak. And this has also been a very crucial method in several experiments like MOA or EROS or OGLE to probe dark matter in the Milky Way. So basically pointing, for several decades, pointing telescopes towards the galactic bulge or towards the Magellanic Cloud and counting how many microlensing events we have, right? This could tell us how many machos basically we have in the halo. And it turns out that dark matter cannot make, from these experiments, cannot make for more than 10% in machos in most of the relevant range, right? 10 to the -6 to 1 solar mass. Microlensing is also responsible for flux anomalies in quasars, but I won't get into that. I'll talk about something similar soon. Okay, so this concludes the introduction. What we have been doing until now in strong lensing in the past 20 years. So dark matter mapping, studying cosmology, and high redshift galaxies. These are the main 3 parts. And with microlensing probing the content of dark matter. Now, a few years ago, several interesting things happened. Namely, the birth of the lens transient science. And we can see that we can do many things with lens transients. We can continue to probe dark matter and its composition on various cosmological scales. We can measure fundamental physics or test fundamental physics. We can do real-time cosmology. I'll talk a little bit about that. We measure the expansion of the universe in real time. And of course, learn about the transients themselves. So I'm going to talk about 5 different sources, 5 different transient sources. The first one is supernovae. In the CLASH program, we have found, this is a work led by Earendel Patel, Or Rao, Steve Rodney, or is in the crowd, finding a few of the first, or maybe the first lens, meaning magnified supernovae, including supernovae type 1a. And the important thing here is that, with magnification, you could push type 1a supernova to higher redshifts and then much better constrain cosmology, or decipher between different cosmology. And then a few years ago, almost, well, 9 years ago, there was this super luminous supernova detected in Penn stars. It made a nice paper. And then shortly thereafter, it turned out that it was actually lensed. This is why it was so luminous. It was actually lensed. The different images of the supernova were not resolved. So you could not do any time delay science, but in retrospect, they understood that what they saw was a lensed supernova. Then going back to this very nice cluster that you already saw, Pat Kelly found this Einstein cross. You see the 4 different points of a lensed supernovae. So this is the first clear case of a lensed supernovae. This is not type 1a, it's more like 1987. But this is amazing, right? So this supernova is lensed 4 times. You can see that this is our lens model, by the way. You can see the critical curves. I'll explain what critical curves is soon of the model, the 4 images. Now this exploded in this spiral galaxy, but this spiral galaxy itself is lensed by the cluster several times, right? So our models told us that it should appear about a year later in a different image of the spiral galaxy. And indeed, we got HST time and we followed it, and a year later, it reappeared in another image of that galaxy. Okay, so there's a way not only to do cosmology, but you can also observe this. You know roughly when the star is going to explode, right? In the different image, and you can find the early light curve, etc., etc. Since then, there have been a couple of other examples of lensed supernovae. This one was published in Science in 2016. This is a type 1a supernovae and found in the PTF. Recently, Steve Rodney published another one in this lensing cluster. You can see the red dot here. And it also has a time delay prediction for several years from now. So I'm sure people will follow it. Okay, the most exciting, or one of the most exciting things for me, I'm not dealing with supernova per se, are lensed stars. Okay? Now, this is something that I, after dealing a decade with strong lensing before this happened, never imagined could happen. I'm still surprised it has happened, but as I will explain to you, it's inevitable. It must have happened, okay? And it must continue to happen. So this is sometimes called caustic crossing events. So let's just define the critical curves and caustics. So critical curves are basically where the determinant of the lensing Jacobian is 0. So this is the magnification value. It's basically where the magnification diverges. This is an imitation, an image I took in the pool. You can see quotes the critical curves here. It's not really the critical curves, but it looks like. And the caustics is basically the projection of these critical curves to the background surface, or in our case, to Earth. Now, this is also a nice story. It's called caustics because in Greek, the word caustics is to burn. And as we know, when we concentrate light areas, it burns things up. This is the architect Giulio Parigi painting from 1600 of Archimedes. So that's no longer in Cambridge, sorry. Archimedes' legend of burning the Roman ships when they approached Syracuse at about 214 before Christ. So that's about caustics. And since these are the critical curves again, since we have, it's a bit faint, but you can see the lensed arc lying on the caustics here, right? So since there's a galaxy lying on the caustics, and there is, of course, relative motion between the galaxy and the caustics, at some point, and if you do the calculation, you'll see that it often stars would cross the caustic. It's inevitable, okay? And this is how it looks like. So whenever there's something that crosses the caustic, the 2 images disappear, right? So it gets highly magnified before crossing the caustic, and then suddenly disappear. And in fact, Jordi Miralda-Escuder had this idea already in 91 and predicted that it might happen, right? And this is how the light curve would look. This is the dashed line is for an infinitely small source, this is how it would look in practice for, let's say, a star that crosses the caustic. And Pat went it again, and in the program that followed supernova Earendel, found that actually on the critical curve, this brightening that could not have been explained. And he dug in the literature and he saw this paper by Jordi and said, oh, this might be the case. And then everybody discussed this. And yeah, we believe this was a nice paper in 2016, I think, of the first lens star. Okay? So this is mind-blowing. We can see individual stars through half the universe. Measure the SED of individual stars through half the universe, not in the Milky Way. Other galaxies have this is completely mind-blowing. But wait, that's not the end of the story. Look at the light curve. It doesn't look as the one I showed you from Jordi, right? It's completely different. Why? Because the lens is filled with stars, right? So it must be prone to microlensing. It's inevitable. So basically, this is a shot I took at my favorite beach. The caustic smooth, right? So we should see fluctuation as they swipe across the source. This is very similar to the well-known quasar microlensing simulations, and basically the basic idea is that we can count the peaks or relate the statistics of the peaks to the underlying mass point distribution of the lens, which we think in large part could be dark matter. So we have a means now to probe what the lens consists of. And indeed, if you do the calculation, it seems that you could do better than the local microlensing experiments. You can push the 10% to 1% and increase the mass range. Okay? This is why we have several programs now to do this, both with Hubble and with James W. And we hope we could say something eventually in dark matter. So there's several other events published since. We continue to find these lens stars. Not all of them are public, but we continue to find them. These are, I won't go through this, but these are some of the things you could do with this. Some cute numbers of how long an event takes, how many you should find. Roger Windows did a nice paper saying you could find POP3 stars and black hole accretion disk with it in the early universe, etc., etc. Now, one question is, are we biased towards seeing faint stars, which are more abundant, or more luminous stars, and perhaps POP3 stars, which are rarer but brighter? Okay, now we know that the radius of a star follows roughly the mass. The luminosity goes like the mass to the fourth. I'm rounding up the numbers, but forgive me, it's still a few orders of magnitude difference. And the thing is that the reason I'm asking it is because when you approach the caustic, right, there's a limit to how much you can get magnified. The bigger you are, the less magnified you can get. This is why this question is relevant. And apparently we're biased towards brighter stars. This is some calculation that we did. So this is, let's say, these are the numbers relevant for HST. Usually we get to 27 IV. So this is the minimum magnification you should have in order to observe which HST a lens star. Okay, now it sounds huge. Usually galaxies are magnified by factors 2, 3, 10. Here we need magnification of 10 to the 4, 10 to the 5 for O and B stars. Okay, but if we do the simulations, and we develop now a nice tool to do the microlensing simulations with Ashish Meena, a postdoc of ours, very, very efficient method. I can tell you about it later afterwards. So basically we do these microlensing simulations using some recursive ray tracing approach, which really makes the computation much more efficient. And you can see, this is where you cross the caustic and then the flux drops, but you can see that the magnification is often more than 10 to the 4, right? So you are bound to see these things, and we are seeing them. Every visit that we go to HST and observe deep enough a cluster, we see one of these stars. Right? That's a bold statement, but this is roughly the statistics that we get for now. So these things really exist. And so we found a few more, and the most notorious one, maybe you've heard about it, was in the news a few weeks ago, led by Brian Winch and then Co. And some of us, is a star at redshift 6.2. So now we see a single star, not only halfway through the universe, we see a single star from the first billion years of the universe. Okay, so this is the star. The caustic passes right through the star. The arc in which it lies at a redshift 6.2, and we do hope that this is indeed the case. So to conclude this part, magic is not only possible, it is inevitable. Questions so far?
So regarding the star, this is a question that came out at the ICG. Well, how did you know that this was a single star and not a cluster?
So there is a calculation in the paper. It could be a binary, for example, but it couldn't be a cluster because a cluster is not bright enough. A cluster would be less magnified, right? Just because it's bigger and it's not bright enough to compensate for the difference in the magnification.
And it will be multiple. It's big enough that there will be two. It would have a binary.
Yes, and all of this is modeled in the paper. Yeah. So there's still a chance it could, but it's most likely not. It could also be something along the way, but we'll know soon from JW. Okay, so another thing to mention is because of the K correction or because of the shape of the black body stars, if you push these stars to higher redshifts, the peak luminosity actually is getting pushed into the relevant filters. My point is we're going to continue to see these stars even to much higher redshift than redshift 6. Okay, we're not losing. The cosmological dimming plays a little role because of the K correction. So it's a competing effect that compensates for this. Okay, let's talk about fast radio burst a bit. A dear colleague from Ben Gurion University has passed away last year, David Eichler. I don't know how many of you know him. He was a true genius. One of the guys that predicted, among many other things, what would be the outcome of two neutron stars colliding, and this verification was, of course, verified in the with LIGO and all the afterglows. And we had a nice paper together, thinking a little bit about fast radio bursts and lens fast radio bursts and what we could do with them. So, of course, fast radio bursts, they are, as you probably know, strong millisecond bursts that are now detected in increasing numbers. This was written even before CHIME and ESCAP, and so now much more than that. And people have written papers about the fact that you could do cosmology with them, you could probe compact dark matter with them, or fuzzy dark matter with them, measure H0 because the time delay, because it's a short burst, the time delay would be known to a high accuracy. And then we thought about doing real-time cosmology with it, and this is a nice little paper we did. So real-time cosmology is trying to capture the expansion of the universe in real time, just in a tiny bit. So observe the universe today, observe the universe a year from now, see by how much things changed, how much things redshifted in the meanwhile. Right, so basically what we want to measure is dz to the t, the change in redshift in time. Now, this is nice, okay? Because it's complementary to measuring H0, right? dz to dt would basically give you h of z. So you could map the Hubble constant through redshift, if you could do that. And you could do that directly. But here's the challenge. The age of the universe is 14 giga years. So that's, let's say, 10 to the 10 years. A human lifetime is, at best, 10 to the 2 years. Okay? Which means that in a human lifetime, you can only measure a 10 to the minus 8 change in the universe. There's no way you can measure redshifts to this accuracy. Okay? So there's no way you could do real-time cosmology. Now, this is the change that you expect in 1 earthly year. You can see that the redshift changes by 10 to the minus 11. This is by how much H0 changes. It was 70 a year ago, and this is how it is today, etc., etc. So that's, of course, negligible. And Avi had a beautiful paper in '98 proposing 2 ways to do that. One is by the, I know some people here are involved with what was called the Codex experiment, so spectrograph, basically measuring the Lyman alpha forest over many quasars a decade apart or a few decades apart, and trying to see by how much it expanded in the meanwhile. The second was to use multiple images or take advantage of the time delay between multiple images to save basically the time that you have to wait to measure the expansion. But both of them haven't been really successful until now, of course. And then recently there was a paper, actually in 1901 there was a different paper saying this, but recently there was also a paper highlighting that when you have a strongly lensed source, multiple image source, and there's a time delay between the 2 images, the time delay itself changes with time because of the expansion of the universe. So it's okay to measure the time delay, but if you could measure the change in time delay, you could measure directly dz to dt. okay? But you cannot measure the change in time delay. It's too slow. It's 10 to the minus 3 seconds. But now we have a source that can do that, right? FRBs are of order millisecond. So with FRBs or a lensed FRB, when you need a repeating FRB to be lensed, but with a lensed FRB, you could measure dz to dt. Okay, that was our paper. I won't take you through the full calculation because we don't have time. But basically, the final conclusion was that we expect with the current rate about 10 repeating FRBs to be lensed by clusters, and many more, perhaps about 10,000 or the 10,000 multiply image by galaxies. So this is possible. There are still some effects that would swipe the signal, such as transverse motion of the galaxies, but this could be, there have been some work that showed that this could be dealt with in several ways. Okay. That's about fast radio bursts. Gamma ray bursts. I guess everybody knows what gamma ray bursts are. I want to highlight two recent results. The first one is work we did a few years ago with Anna Barnaka and Margaret Geller at Harvard. A very cute idea. Basically, this is not a gamma ray burst, it's a gamma ray source. It's a blazar that is multiply imaged, and you can make a lens model. The basic idea is you make a lens model, a simple lens model for the two images that you see, very easy. And the lens model tells you what the time delay should be for that source position. Now, there were two flares for which you could measure the time delay, and it didn't fit exactly what the model said, but it did fit what the model would say if the engine were slightly apart from the main central part of the source. By measuring the time delay and how it changes with different flares, you can learn about how far away the flare origin is from the central engine and what is its movement by in other words, right? So there's the radio core and the moving towards the central engine. There was also a prediction that I'm not sure if we followed up on or not, but it's a cute little result. And in the past year or two, I think it's only from 2021, there was the first detection, actually 3 or 4 since, of lensed gamma ray bursts. Okay, this is only in the past year. If I had given this a year ago, there wouldn't have been any lensed GRBs, but now there are about 4. Some of them slightly debatable, but some of them seem legit and seen in different experiments, not only in one. So you can see it in some of them you can see in Swift together with the GPM or Fermi. So there have been several of these. And the point is that you get intermediate mass black hole masses for these objects according to the time limit. Okay. Now, we don't know where these are. We don't know that. This is why there's the 1 + z factor here. We don't know where this object sits along the way because we don't see it. And we don't know exactly where the GRB came from. But we do know roughly what should be the mass, and this can be a nice answer to the intermediate mass black hole problem. Okay, the last thing are gravitational waves. Of course, a new field in astronomy, or maybe it's not astronomy, but a new exciting field. And of course, this is why it generated so much interest. Also in terms of lensing, there have been a lot of papers and a lot of works about the lensing or possible lensing of gravitational waves. There are two main results that I want to highlight. The first one is a very, very nice discussion by Tom Broadhurst, Chema Diego, and George Smoot, highlighting the degeneracy between the chirp mass and the luminosity distance, or in other words, saying that just by the measurement of the gravitational wave, we cannot know if the object is high mass, which is close by, or smaller masses coalescing, which are farther away but magnified. There's no way to know. It's inherently degeneracy. And what they say is that if you take what they say is non-lensed is the basically distribution of X-ray binaries, the masses of X-ray binaries in the Milky Way. If you take this distribution and you lens it, you get the distribution that LIGO gets. Right? We don't know how come there are so many 30 and 40 and 50 and 60 solar mass black holes that LIGO found, but it could be the same population as we have in the Milky Way, but lensed. Okay? And at higher redshifts, at distant galaxies. So this is one nice solution that they're highlighting. It has several problems, but it's still a very nice thought. One of the problems is that the mass function has to be so steep to gain so much from lensing, right, that it doesn't make much sense. It completely deviates from how you imagine the star formation rates through history, the historical star formation rate or the Mabdao plot. They do say that, you know, in their favor, that with sub-millimeter galaxies, it's been the same case, that you first detected the very luminous ones. And another thing is they say that this fast evolvement that they see goes hand in hand with how globular clusters evolve from redshift 1 or 2 to now. So, you know, it also explains the lack of many spins or of extreme spins that you see. So there is something to it, which is great. Two other things I'd like to mention, and that would be the final couple of slides, is that, you know, this is a great question, right? It's very intriguing. So it would have been cool if there were a way to know if a gravitational wave is lensed or not. A gravitational wave signal is way to know. And apparently there is. Yes, there have been several works led mostly by Dai, based on previous works by Takahashi and others. And the main idea is that you could, if you have a lensed gravitational wave, let's say you have 3 different images, each one has a different symmetry. Since this is basically there's something that's called the Morse phase. I won't get into the math, but there's something that calls the Morse phase that can tell you which type of image it is according to the Fermi potential, which means you could know in some of the cases if this is a lensed gravitational wave. The other thing I would like to mention is this is relevant to all these transients we talked about, is that we have to be careful that all of these effects are assuming geometrical optics. But in some of these, this approximation breaks. You have to take care of wave effects. This is a demonstration, and with this I will end, of a caustic map that we did to simulate one of these lens stars. Right? This is how it looks. But in principle, what happens in practice, and this is some experiment somebody did online with a pointer like this and a drop of water. And you can see that because of quantum effects, of course, you get these fluctuations, right? And the size of the fluctuations is similar to the George Airy ring calculation, which is, of course, also related to Cambridge, tells you if you should worry about these things also for cosmological sources or not. And it turns out that for most of them, this from what we know under, this is from a Guri's nice paper review, on most of them, we shouldn't worry about it, at least from what we know now about the source size, but they are very relevant for gravitational waves, and there are a lot of works that now deal with that. So that's about it. I won't go too much through the summary. I just want to mention that I haven't almost mentioned JWST. We have many programs with JWST now, we as a community, and also I'm a member of several, to do all of these science, including searching for lens stars, lens supernovae, studying the first galaxies, ionized bubbles, etc. And yeah, let's hope for the best. I hope we'll get some nice results soon. So thank you.